orbiting in days, and the ultra fastest ones are orbiting in less than a day. So their year is less than 24 hours. They are whipping along. And so these are all multiple planet systems, mind you. None of these are single planets, they all have multiple planets. There are systems where you can find 3 planets that all have orbits less than 10 days.
It's like on the left now. It's like
so nature does things that we never would have expected unless we were actually looked at other planetary systems. And so one of the strangest planets that was found first is called Kepler 10b. It was the 10th Kepler planet. This has a day-side temperature of about 4,000 degrees Fahrenheit. You might wonder how it could be that hot. Well, if you're in a 1.5 day orbit, your day side is going to be that hot. And this rocky planet probably has a permanent molten lava day side. The whole day side is probably a lava ocean. It's probably, well, we don't know it's tidally locked. There's no way to tell, but we think, just like the moon always shows the same face to the Earth, we think this planet always shows the same face to its star. And so this is an artist. Oops, come back. This is an artist. Come back. This is an artist's rendering of what it might be like to be at Kepler 10b. We obviously don't know what it's like, but this is to scale. So you know, the sun takes up a tiny fraction of our sky, right? The sun is about the size of, I don't know, like your thumbnail. And so this planet's so close to its parent star that the sun actually takes up about. Its sun takes up about 10% of its sky because it's so close in. And so we can fly around and maybe it looks like that. It's definitely a rocky planet because we know from its mass and radius. We know its bulk density is a density higher than that of the Earth. It's a rock iron planet. And we can imagine flying there. And in a minute we're gonna cruise through some of the lava ocean valleys on the day side. And so one of the things that Kepler has shown us is that you really, not too commonly, but you do sometimes find planets in 1 day orbits or a few day orbits. Another one that was, in some sense, kind of like an Earth analog, in that it was very similar in Earth to its mass. So we're, of course, at 1 Earth mass, 1 Earth radius. This is Kepler 78b. 1.7 Earth masses, 1.2 Earth radius, very similar. But we're in a 365-day orbit. Kepler 78b is in an 8-hour orbit. So it doesn't touch the surface of the star, but it's orbiting at about 5 stellar radii away. It's extremely close in an 8-hour orbit. And so one of the things we really can tell is that nature is a lot more imaginative than we are in the sorts of crazy planets that it makes that we don't have in our own solar system.
Are those orbits decaying?
The orbits probably are decaying due to tides, but we don't have a long enough tide baseline to see that. Perhaps the most important system that was found in terms of really changing our view of what planetary systems might be like was called Kepler 11. And this was discovered in 2011. It made the cover of Nature, which is a famous science publication. And it has 5 planets orbiting within the orbit of Mercury. And they're all more massive than the Earth. Okay? 5 within the orbit of Mercury's distance, where we have nothing. This has 5 planets, and they're all more massive than the Earth. Most strangely, the parent star looks almost exactly like the sun. It's the same mass and radius as the sun. It somehow ended up with a planetary system that doesn't look anything like our own. And we still don't know why that is. We don't really know why these things happen yet. This is what Kepler data looks like. It's kind of a mess. This is time in days, 0 days, 100 days, 200 days, 300 days. This is what the raw data looks like. It's kind of messy. There's weird events that happen. If you're really good at data processing, which I'm not, I'm mostly a theorist, by the way. If you're really good at data processing, you can, this is the brightness versus time. This is constant brightness. And sometimes there's weird anomalies where the spacecraft shuts off, or it's pointing the wrong direction, or there's safe mode. But what you actually see is this hair, this rain. And what that is planets passing in front of the star, blocking out a tiny amount of the parent star's light. So this is 1 part in 10,000 right there. 1 part in 10,000. And you can see all these planets, and they're all color-coded here. So the red ball is a planet that transits every 13 days. The gray ball transits every 100 days or so. And over here, there's a triple transit, 3 planets transiting at the exact same time. This is what the artist was trying to show here. 3 planets passing in front of the parent star all at the same time. Yeah, sure.
In that system, are they harmonics of each other?
The planets do not appear to be in resonances. No, they're not. The satellites of Jupiter, for instance, the Galilean satellites, one is in a period exactly twice, and the next one is exactly twice, and they perturb each other. And we do see that in some systems, but in this system that is not the case. No question. So the Kepler-11 also has an artist's conception, and so this is the transit events. And so there's 5 planets inside the orbit of Mercury, and then there's a 6th planet a little bit further out. In this movie, the planets are exaggerated in size a little bit, so you can see them, and they also leave these cool smoke trails. So we can see them go around as well. And so this guy here is between Mercury and Venus, essentially. These guys are all interior to where Mercury would be. One of the things that I think about when I think about the Kepler-11 system is how closely packed in the planets are. And so we didn't definitively know, you might say, that the sun was the center of our solar system until people built telescopes. So Galileo in the 1600s was able to point his telescope at Venus, and he could see that Venus had phases. You could see that Venus was a crescent sometimes, and you can't tell that with your eye. And so he was able to show definitively that Venus orbited around the sun, that the Earth was not the center of the solar system. One of the things I imagine sometimes is if Venus was, let's say, 3 times bigger, or Venus was closer to the Earth, we would have been able to tell since the dawn of humanity that Venus had phases. And we would have known in the whole history of time that the sun was the center of the solar system. And instead, we were stuck with this idea of the Earth being the center because we couldn't see the phases of Venus because Venus is so small and far away from us. But you can imagine other planetary systems with maybe an Earth-like planet that did have a bigger neighbor closer by. And you could tell that that planet would have phases, and you'd know from the dawn of humanity that the sun was the center of the universe. And just it's amazing to think about how the history of thought, since thought began, might have been different if we always knew the sun was the center of the solar system.
Only would have made a difference to Galileo.
Well,
Or maybe Copernicus.
So another one of my favorite systems is called Kepler-16. And so there's a famous movie some of you may have heard of called Star Wars. And so this is probably the most iconic picture from the movie, one of the most iconic ever. So this is a small desert planet that has 2 parent stars. So Kepler-16 is not exactly this system. Kepler-16 is a Saturn-like gas giant, but it was the first planet found that has 2 parent stars. And this is, again, an artist's conception. One of the crazy things is that this planet does have a yellow star and a red star, very analogous to what George Lucas thought up for Tatooine. So in that sense, he was, well ahead of his time. And there's a little movie of that also. NASA headquarters is very good at making cool animations of the systems that are found. So this is a Saturn-like planet. It's warmer than Saturn. It's in about 100-day orbit, so it is still pretty close in. But it does have 2 parent stars. This is a Sun-like star called a G star. That's a faint M star, it's a faint red dwarf. So this star is actually 100 times brighter than that star. So in terms of the temperature of the planet, it doesn't really care about this other star because the yellow star is so much brighter. Yeah.
Do you have any examples, or have you ever discovered something similar to that, but opposite, where you have 2 planets in orbit around their similar gas and dancing around the
Yeah. Well, okay. So The Earth-Moon system is to some degree like that, although the Earth is a lot more massive than the Moon. So no one has found a twin planet system like that in the Kepler data, where you can imagine, let's say, two Earths of similar mass going around each other. No one's seen that yet, but people are certainly interested in looking. People are certainly trying to see that, but it hasn't popped out. It would be pretty easy to, if such things existed within 100 days of the parent star, they would be not too hard to see. We haven't seen any. Okay, there's a question over here, I guess.
Ready for it?
Pluto and Charon are also an excellent example. They are very similar in mass. Very, very good thing to point out. One of the things that's cool about the Kepler data is that it's all public now. All the Kepler data is public, and I think we're up to 6 planets that are found with 2 parent stars. Those are called circumbinary planets. 4 were found by the Kepler team, but 2 were found by just regular people who were looking at Kepler data. So there's a website called planethunters.org, and at planethunters.org you can actually look at Kepler data, brightness versus time, and there's amazing software, and you can pick out planets. Because sometimes, even though computers are really amazing, sometimes the human eye is better at picking out patterns than any computer program. And so Planet Hunters has found, I think on the order of 10 or 15 planets that the Kepler data pipeline has missed. And the Kepler pipeline is especially bad at these circumbinary planets because they're not very regular, because sometimes it'll pass in front of the small star or the big star, and then later on the 2 stars will have changed positions, so that it won't be very periodic. And so in that case, the human eye might be better at finding planets than computers are. So planethunters.org is a cool site to look at.
So is the smaller star always orbiting the larger star in those systems? Or?
Yeah, the 2 stars orbit around their common center of mass, like on a seesaw. There's some common center of mass where everything's balanced. So if there's a smaller star, it'll always, to some degree, look like the smaller one's orbiting around the big one. But if they're very similar in mass, they'll look like they're just orbiting around each other. Okay, so I want to move on to the last part of the talk, thinking about how common potentially Earth-like planets are. So I want to come back to the habitable zone. So the habitable zone, and here is this happy green region where maybe we could have liquid water on the surface of a planet where it's just the right temperature. People sometimes call this the Goldilocks zone. You might imagine why. So if you have a hotter star, the Goldilocks zone will be further away. You'll have a brighter campfire. If you have a smaller, fainter star, a dimmer campfire, you'd want to be closer in. You have a smaller habitable zone closer in. And so one of the most interesting Kepler systems is called Kepler 62. Again, not a very great name, this is our own solar system. We've got Earth here. And in the Kepler 62 system, there's 5 planets, 3 of them insanely close to their parent star in like 20-day orbits or less. But there's also Kepler 62e and f, and these are planets that are about 1.5 Earth radii, so maybe potentially Earth-like, that are in the habitable zone of its parent star. And this parent star is a little bit smaller and fainter than the Sun, so the habitable zone is closer in. One of the powerful things about Kepler, though, is that it's not really designed to look at individual planetary systems. It can find really cool individual systems, but it's really a statistics mission. It's trying to find thousands of planetary systems to answer the question whether or not an Earth-sized planet in an Earth-like orbit is a common thing or not. So that's what we want to talk about next. So astronomers classify stars by an archaic system developed over 100 years ago that we're stuck with today. And so this is an O star. An O star is a really massive, bright, hot star, very rare. As you go to smaller and smaller stars, they become more and more common. So the Sun is a G-type star. And if anyone ever told you that the Sun is a normal star, an average star, they weren't really being honest with you. I won't say they were lying to you, because they probably didn't know better. But there are stars much bigger than the Sun. There are stars much smaller than the Sun. So you might say, okay, fine, that makes the Sun kind of average. But these small faint stars, these M stars, make up 70% of all stars. And so these stars down here, these faint guys, are the vast majority of stars. And these big stars are the vast minority of stars. And so if we want to know what the most common kind of planetary system is, we should try to figure out what the most common kind of planetary system is amongst those small stars, because they're 70% of all stars.
How do you know the second?
Look at them a second. Okay, I'm getting a little hoarse. I read about a half hour of James the Giant Peach earlier tonight, so, all right. So, within 30 light years of the sun, we have a very complete census of stars within 30 light years of the sun. We can actually go beyond that and have a good census too. Within 30 light years of the sun is a G star. There's about 20 other Gs like the sun. There's none of these O and B stars. That's probably good because those guys would supernova and blow us up someday. But 246 of them are these faint red M stars. We can see them. They're the most common kinds of stars. And so Kepler mostly focused on sun-like stars because he was trying to find planets that you might think might be exactly like the sun. So Kepler is mostly focused on these guys, but also returned a lot of data on these guys as well. And so this is the only kind of really, this is the only plot I took from an actual scientific paper, but I think we can get through it. This is the number of planets per star for planets around these M stars within 50 days. So again, we don't have anything within 50 days of our parent star. It's totally empty. But nature doesn't make any big guys around these small stars. But then as you go to smaller sizes, below about 3 Earth radii, you start to find planets. They pop up a lot. And so what Kepler has shown us around these faint M stars, which makes 70% of all stars, they have about 1 planet per M star within 50 days, and about 2 planets per star within 100 days.
What do you mean by within 50 days within 100 days?
A 50-day orbital period. Yeah, so we're at 365, Mercury's at 88 days. So around these small faint stars, they very commonly have 1 or 2 planets within a Mercury-like orbit. So they make small, compact planetary systems. So when you analyze all the Kepler data, you look at the 150,000 stars that have been looked at.
So when you go back to that other graph,
Yeah.
where's the green star? Like, where's the green zone?
Ah, okay, right. So the habitable zone, right. So for these M stars, the habitable zone is kind of 20 to 40 day orbits because they're faint, so you want to be close to them. And so there are a lot of these, so it's not possible to cut this diagram exactly the way you want it, but all these planets are in or close by the habitable zone. Yeah, yeah. So if you look at all the Kepler data, 150,000 stars, you know just from geometry you're missing most of the planets because most of them are not edge on, but that's simple geometry. You can calculate what that would be. What we know from what most of the Kepler data is now analyzed, that about 10% of sun-like stars have an Earth-sized planet. The definition of Earth size is kind of, let's say, 3/4 the Earth, so maybe 1.5 times the size of the Earth. And that's limited by not having many planets detected out there. Those planets are very hard to see because they're in 1-year orbits. So there's not a lot of actual detections out there, but it looks like about 10%. And so that number probably won't change by a factor of 2. So a rule of thumb in the back of your mind might be that for sun-like stars, stars like the sun, maybe only around 10% have an Earth-sized planet in this Goldilocks zone, in the habitable zone. If you go to M stars, which are again 70% of all stars, 25% of them or so have an Earth-sized planet in the habitable zone. And so M stars are 70% of all stars. There's 100 billion stars just in the Milky Way galaxy. So that's 70 billion M stars. If you take 25% of 70 billion and then throw in these as well, you get a number, plus or minus 50%, which in astronomy is fine, of about 20 billion habitable zone, Earth-sized planets in the galaxy. And so what's amazing to me is this is a number that for centuries in human history, we've wondered what this number was. And so NASA built a telescope that answered this question. And so what we want to do now is think about how we can learn more about these planets and maybe find some that are nearby. Because these Kepler systems are all kind of far away. And it was designed to look at a large sample of stars far away. So in the last 5 minutes or so, I want to talk about what we might want to do next to learn more about these potentially habitable planets. Okay, run a little bar. Okay. Finding another blue marble, right? So people talk about Earth as like a blue marble. So we want to find some close-by examples, because Kepler doesn't find close-by examples, it finds far-away examples. But astronomers are really excited about finding nearby transiting Earth-like planets. So there's been a lot of missions. So Kepler, you might have heard Kepler broke maybe about 1.5 years ago. That's not entirely true. It still works pretty well. So that's called the Kepler K2 mission. I could talk about that after my talk if you want me to. I have a couple of backup slides. And so that's looking in the ecliptic. That's looking in the signs of the zodiac, looking for planets. And so that'll probably find hundreds of more planets. There's also a European mission called CHAOPS. There's something called TESS. TESS is another NASA mission that's going to be an all-sky survey for transiting planets. Whereas Kepler looked in one patch of the sky, TESS will look at all the stars in the sky, at least all the bright ones, trying to find planets. So that'll only find nearby planets. That'll be really exciting. And there's Plato, a European mission, which is kind of like Super Kepler plus Super TESS. It's going to do both things really well. That's going to be in 2024. That's about 10 years away. So the powerhouse is going to be TESS plus the James Webb Space Telescope. And I'll get to that in a second. So this is a picture of Earth as taken by the Cassini mission, which is at Saturn, right? This is what Earth looks like as seen from Cassini. And of course, Saturn is very close by, astronomically speaking, right? So this is a pale blue dot of what Earth looks like. So in principle, you could try to take a spectrum of what Earth's atmosphere looked like and try to find signs of life. And so if you want to do this for a transiting planet, you want to use the geometry to your advantage. This is a picture of Venus passing in front of the sun. And so what this is, what is causing this effect? That's Venus's atmosphere. There was an astronomer named Lomonosov in Russia in the 1700s who, I don't know how he was able to do this, he detected that Venus had an atmosphere with a fairly crude telescope. This is a space telescope, mind you. But if you can actually potentially take a spectrum and look for absorption features in the planet's atmosphere during a transit, you might be able to see molecules in the planet's atmosphere. We've done this already for gas giants like Jupiter. We've detected water vapor, sodium, potassium, methane, carbon monoxide, carbon dioxide. This technique really does work for gas giants. We don't have the technology yet to do it for small planets, but we really want to in the future. So this is the James Webb Space Telescope. It launches in 2018, October 2018. Kepler cost about $600 million. James Webb is costing $8 billion of our money. But it's a phenomenal multi-purpose instrument. It's essentially the Hubble Space Telescope replacement. And it'll find the most distant galaxies at the dawn of time. It'll also be able to take spectra of small planet atmospheres, probably not quite Earth-sized planets, but planets maybe a little bit bigger than Earth. And it's going to be looking for this effect there.
I think
it's 6.5 meters, which is like 20 feet across, which is too big to fit inside of any rocket ever made. So it has to launch and then unfurl and unfold in space. And it's going to be out quite a ways from Earth. So Hubble is in a low Earth orbit, so we can go and fix it if it breaks. James Webb is going to be out at what's called the L2 Lagrange point, way away from Earth. So it has to work because we can't go fix it. And I think it'll work. Lots of astronomers spend all day, really, really wanting it to work. And it's going to be a phenomenal instrument that's really going to be transformational to all phases of astronomy. And so the things you might want to see, for instance, are molecular absorption features. So the atmosphere of Earth has water vapor and oxygen and ozone. The atmospheres of Mars and Venus have mostly just CO2. This is kind of a schematic. So these are the things we'd want to see in an atmosphere. that's where we're moving to in the future, is going beyond just detecting planets and maybe trying to characterize what they're like. So my concluding thoughts are that nature is a bit more creative than we are, say for George Lucas when imagining worlds. We're only just beginning to understand how planetary systems are built. We only in the past couple of years have the real data of what the average planetary system looks like, and it does not look like our own. We don't really know yet what that means, but it means something important. There's really good evidence for tens of billions of planets in the habitable zone in our galaxy. That number I said is about 20 billion. That's probably right, within 10-20%. Our planetary system is perhaps a bit rare, and that is not a typical layout. However, in other ways, it's kind of common in that we know Earth-sized planets in the habitable zone are common. They're just a lot more common around these faint M stars than our star. And the next stage is to characterize the planets themselves. This is going to take a lot of money, a lot of time, and a lot of patience. Because the James Webb will make some progress, but if we really want to be able to say something definitive about life on another planet, James Webb is not going to do that for us. We really are going to have to get behind the next or even next generation space telescope to do something like that. So to conclude, I really like this image again of we have the outline of what other planetary systems look like. Just like in 1550, we had the outline of what North and South America looked like, but it took hundreds of years of exploration to know what was in those continents, what the rivers were like, what the streams were like, what the people were like. And in order to understand other planetary systems, really what we have now is just the broad outline. We know the planets are there. We know what planetary systems look like, but we really don't know what the planets themselves are like. And so it's going to be the next decades and hundreds of years of astronomy and astrophysics that are really going to go into trying to understand what other planetary systems are like and to characterize those planets. And so thanks a lot for listening. Yeah, sure.
So, in our solar system, I think most of the planets orbit all in the same plane. Is that true with other planetary systems?
So the question is, in our planetary system, all of the planets orbit in about the same plane, and we also orbit in the plane of the sun's equator, which is also important. And so that gave rise to the idea that's hundreds of years old now, that there was a disk around the sun, and the planets formed out of that disk of material that coincided with the star's equator. So it's a little bit hard to answer that question with transiting planets to some degree, because we definitely see systems where the planets, we see multiple planets all in the same plane. And sometimes we can even measure where the star's equator is. And so we can definitely see systems where all the planets orbit in the star's equator and they all are in a disk. But the hard part about transiting planets is that sometimes there could be planets that you couldn't see. We might see one or two planets that are in the plane, but if there's a planet that's even misaligned by 5 degrees, it wouldn't even have to be a lot, you would miss it. And so people have spent a lot of time trying to answer that question from Kepler data. And so it seems like most planets are aligned, but we can't really get a definitive answer on that question.
Is that important?
It's really important to understand planet formation, for sure. We do know sometimes we can see planets that are in crazy orbits, that they orbit over the pole of the star rather than the equator. And so that's been suggested that if you have multiple planets that maybe form too close together, one might get tossed in on a crazy orbit, one might get tossed out. But I wouldn't say we have enough statistics to build up a coherent understanding. That's still a work in progress. Good question. Yeah, sure.
The largest planets that Kepler has found inside the universe, are any of them gas giants?
The question is, planets inside the orbit of Mercury, are any of them gas giants? Yes. We now know that about 5% of Sun-like stars have a gas giant planet within the orbit of Mercury. And so no one has figured out a way to form a gas giant planet that close in. We think gas giant planets more commonly are only formed further from their parent star where it's cooler. And so that has been taken as really strong evidence that planets can move after they form. And we don't really know why that is. The two leading theories are that if you have multiple planets, they might perturb each other and one might get tossed in and one might get tossed out. Another idea is that the planets form fast enough while that disk of dust and gas is still there, they might feel a drag that can drag them in closer to the parent star as time goes on. But you can find gas giant planets in one-day orbits, and you can actually see clouds of gas coming off of them like they're evaporating.